Ampere's law of force. Ampere's law of force. Ampere's law of force. Ampere's law of force. It states that the force between two parallel wires carrying current. It states that the force between two parallel wires carrying a current is directly proportional to I1, is directly proportional to current 1 and current 2, and inversely proportional to the square of the distance. This implies this is directly proportional to I1 and I2 and inversely proportional to the square of the distance. This implies force is directly proportional to I1, it's directly proportional to I2, and it's directly proportional to 1 over R2, and this one can be summarized as force is equal to K into I1, I2 over R squared, where F is the force, I1 and I2 are currents, I1 and I2 are currents, and R is the distance, and K is equal to a constant. K is given by K is equal to mu over 4 pi. So replacing this into the above equation, then K force, or replacing this into the equation of force, force is equal to mu I1 I2 over 4 pi R squared, and mu is equal to mu naught mu R, where mu is equal to permeability, and mu naught is permeability of free space, which is equal to 4 pi times 10 to power minus 7 henries per meter, and mu R is the relative permeability. We can stop there for a while. Force which you've calculated, the force is attractive, write that. The force is attractive. After this equation, write the force is attractive when the currents are flowing in the same direction. The forces are attractive when the currents are flowing in the same direction, and repulsive when the forces and repulsive when the forces are when the currents are traveling, not when the forces, when the currents are traveling in the opposite direction, and repulsive when the forces are, when the currents are traveling in the opposite direction, and repulsive when the currents are traveling in the opposite direction. Full stop. The force which one current exerts, the force in which one current exerts on the other is given by F is equal to mu I1 I2 I1 I2 over 4 pi double integral of change in length 1 times change in length 2 over r squared, where r is the distance, over r squared, where r is the distance, and you have to multiply it with the direction, which is a of r, where force is the current exerted due to I1, full stop. Then write force between two long parallel wires. Force between two long parallel wires. Let the change in force dF1 be given by dF1 is equal to I1 dL1 times B2. Let it be given by when the force is exerting a current, there will be a current induced in the next coil. Quite okay. These are two windings of, like the two windings of a transformer. You expect that if this current is here, it will reach here as I2, and the I2 will be the induced current. Quite okay. Will be the induced current. So whatever we are going to do is that dF1 is given by I dL1, which is going to induce a current in B2. The B where I1 is current flowing in first section, and dL1 is the change in length, and B2 is the flux density in coil 2, due to coil 1, But flux density B is equal to mu H. Let's call this one here equation 1, and let's call this one equation 2. Replacing equation 2 into 1, change in force dF1 will be equal to I1 change in current and length times now mu 2H2. Also H is equal to, and because what I would have said B is equal to mu H, and where mu is permeability, and H is magnetic field strength. Let me call this one my third equation. So I can say magnetic field strength is given by H is equal to Ni over L, where, let me call this one my equation 4, where N is number of turns, I is the current, and L is the length. Replacing equation 4 into 3, I get dF of 1 is equal to I dL1 times mu 2 into N2 I2 over L2. This can be written as dF1 over dL1 is equal to I1 times I2 times mu 2 into N2 over, this was L2, this is L2, not L squared, L2 over L2. But what we can say is that we can still say that let the number of turns B1. So the formula will be reduced to dF over dL is equal to I1 times I2 times mu2 over L2. The field in a magnetic circuit, the field in a magnetic circuit is circular. This implies that L2 is equal to 2 pi r. So the formula, this implies dF1 over dL1 is equal to I1 I2 mu2 over 2 pi r. That is the force in Ampere's law. That is the force in Ampere's law. Let me introduce you to force on a current element. Force on a current element. On a current element. Force on a current element. Force on a current element. To find the force, to find the force on a current element, to find the force on a current element I dl, I current times change of length, from volume current density, that is J is equal to PV dV. J is equal to PVU, not PV dV. J is equal to PVU, where J is the current density. PV is the charge constant, and U is the velocity, we have current distribution similarly to those ones of charge distribution, where we have in charge distribution we have Q is equal to PL dL, Q is equal to PS ds, and Q is equal to PV dV in a volume. We'll have to. I've said that in charge distribution, you have Q is equal to PL dL for a line, and PS ds for surface, and Q is equal to PV dV for volume. So similarly, in magnetostatics, we have current distribution. We have I dl, the one we were looking at. This is continuous line distribution. This one is continuous line distribution, and then we have K ds, which is continuous surface distribution. The continuous current, line current, line current distribution, and this is continuous surface current distribution. And then we have continuous J dV, which is continuous volume current distribution. So we can be able to equate the IDL and equate it to J dV. We can be able to equate it with J dV. Quite okay. We can be able to equate IDL and J dV. Quite okay. So that IDL, I can be able to equate IDL with J dV. So that IDL, I can replace this J with this equation here and get it as PV of U dV. PV of U dV. PV of U dV. PV of U dV. And remembering PV, and remember, according to Gauss' theorem, PV dV can be the divergence of D dV, or PV dV can be equal to the charge enclosed, which is equal to Q. PV dV can be, according to that one, which this one is dQ, because Q is PV dV. Q is equal to PV dV. So PV dV, Q is equal to the integral of PV dV. So PV dV will be equal to dQ. Quite okay. Will be equal to dQ. Are we together? Are we together there? PV dV is equal to the divergence of dV, which is equal to dQ according to the Gauss law. Quite okay. So we want to equate this equation. We can be able to equate this equation, write it, or we can be able to write it properly and say IDL is equal to Q is equal to QU. Is it QU? Yeah, PV, this is PV dV, this is QU is equal to QU. Remember, U is equal to velocity. U is equal to the velocity, and U is written as change of distance or change of length with time. So I can write this equation as IDL into, let me call the dx dl. Let me call it the dx dl, so that this one now, this one can be written as Q into dl times dl dt times dl dt. The dl and dl will go, so that Q is equal to I dt, which is the formula of charge, which can be written as Q is equal to IT, which can be written as Q is equal to IT. This is how you get the formula of charge. We can stop there. Ampere's law, we are continuing with this one. From Ampere's law of force, dF is given by IDL times B. So for continuous current distribution, for continuous current distribution, we have 1 dF is equal to, force is equal to I dL curl of B, I dL curl of B for continuous line current distribution, and we have to force is equal to surface K ds curl of B for continuous surface current distribution, and also we have 3, force is equal to volume J dV curl of B for continuous volume current distribution. And I think that ends the one on Ampere's law. So we can look at Biot Savert. We can look at Biot Savert law. We can now look at Biot. We can now look at Biot Savert law. Biot Savert law. Can hold. It states that the magnetic flux density at any point P due to the differential current IDL is proportional to the product of the current element IDL and the sine angle theta, sine angle theta between the current element and the sine angle theta between the current element and the line joining the element at P and the line joining the element at P and the line joining the element at P, and inversely proportional to the square of the distance. And the distance is given as always as r squared. So we can summarize this and say dB is proportional to IDL, is proportional to sine theta, and is proportional to 1 over r squared, where dB is equal to K IDL sine of theta over r squared, and K is equal to mu over 4 pi, which implies dB is equal to mu over 4 pi IDL sine of theta over r squared, which can also be written as dB is equal to mu IDL over 4 pi r squared curl of A of r, where mu is permeability, and mu is equal to mu naught mu r. Mu naught is permeability of free space, which is equal to 4 pi times 10 to the power minus 7 Henry per meters, and mu r is the relative permeability I dl is the current element, r is the distance, and sine, when you write it, you can write it like this, or you can remove it and write it like this. It is all the same. And sine theta is the angle subtended by IDL and the line joining P. This can be summarized in a diagram as shown below. This is the current element IDL, and it is making an angle theta with the line from where dB is, and the distance between this one, the line and the dB is the r, or we can let it be the r. So and what else? This is IDL, this is the angle, this is the r, and this is the flux density which is entering into the page, I can still say the direction of flux density is given by the Koch cork, screw, rule, and in this case, it is clockwise. It is clockwise. It is, in this case, it is clockwise. The current distribution can be configured into three different distributions, and these are: 1, IDL, which is equal to line, not line, but continuous line current distribution, and 2, KDS, which is continuous surface current distribution, and lastly we have JDV, is continuous volume current distribution, which implies IDL is equal to KDS is equal to JDV, and B is the vector flux density. B is the vector flux density. And from Biot Savert law, we can conclude that B is equal to the integral of mu IDL over 4 pi into modulus, let me write it as R squared times curl of A of R for continuous line current distribution, and 2, B is equal to mu KDS over 4 pi R squared curl of A of R for continuous surface current distribution, and lastly, B is equal to volume J dV over 4 pi r squared, curl of A of R for continuous volume current distribution. Full stop. We can end up there. Yeah? Unasema? Nimesahau mu hapa. Oh, there is a mu here for B. There is a mu J dV. Mu J dV. I've forgotten about that. So we can end up there, and we'll continue from there next time. There is an example, but it will take a lot of your time, and then we go to analyze diagrams next time.